Okay guys, week 10 physics CA. Okay, this question, in order to charge a glass rod, it must be rubbed against silk. Let me tell you guys why. Look. Let's say they have to be different materials. Okay, so let's say you have a glass rod, it's positive, and another glass rod, it's negative. They wouldn't charge each other, they just both become neutral. If they're both positive, nothing would happen. If they're both neutral, nothing would happen, right? So if you want to actually charge something, they have to be different materials. This because different materials, they have like different tendencies to hold the electrons. Okay? Two metal rods A and B are mounted on an insulating block aligned along a common axis equally spaced. These rods are oppositely charged and equal in magnitude as shown in the below diagram. A light neutral sphere is a conducting with a conducting coating suspended by a long insulating thread is introduced to the space between the rods. What will happen to the sphere? It will remain at rest. Because guys, the electrons are going to be attracted to this side and the positive charge is going to be at this side, yeah? But see, they're both equal magnitude and they're equally spaced and it's dropped in the middle. So this would pull equally and this would pull equally. So nothing would happen. The forces would cancel out. How many electrons should a neutral object gain or lose in order to acquire a charge of 7.4 times 10 to the power of 9 Coulomb? Okay guys, look, there's a formula. Q, which is coulombs, equals number of electrons times the charge of an electron. So this is the number of electrons. I'm not gonna write it all, number of electrons. And this is the charge. It's 1.6 times 10 to the power of negative 19. Okay, so we have the charge, which is here. So it's gonna be 7.4 equals 7.4, wait, 7.5 times 10 to the power negative 9 times 10 to the power of negative 9 equals n times 1.6 times 10 to the power of negative 19. So just do it on your calculator, shift solve. 7.4 times 10 to the power of negative 9 equals x times 1.6 times 10 to the power of negative 19. You get n equals 4.625 times 10 to the power of 10. What's this? I can't even read my own hand. 4.6 times 10 to the power of 10. Okay. 4.6 times 10 to the power of 10. In a typical lightning bolt, an estimated charge of 20 coulombs is transferred from a cloud to Earth. How many electrons make up that lightning bolt? So guys, it's the same. It's gonna be Q equals N times E. Q is 20 equals N, we don't know it, and E is 1.6 times 10 to the power of negative 19. So also this one, just do it on your calculator to find N. So 20 equals x times 1.6 to the power of negative 19. wait, the cat's taking some time. 1.25 n is gonna equal 1.25 times 10 to the power of 20. Oh, 1.5. Okay, 20 coulombs, 2 coulombs, 2.0 coulombs. Okay. Leave the negative terminal of a 1.5 volts dry cell to the positive terminal through a thin wire. The amount of heat energy released. So guys, energy is coulombs times the volts. Okay? A coulomb is actually just, yeah, coulombs times volts. So 2 times 1.5, you get 3. So it's going to be 3.0 joules because two significant figures. 3.0. Where does this energy come from? The energy doesn't come from the wire and the energy doesn't come from the electrons. The energy comes from the dry cell. A battery, basically. Okay. Storage in a battery, it's chemical potential. Thermocouple, it's heat energy. Electrical generator, it's mechanical. And the photoelectric, it's light. Okay. The energy that 1 coulomb of charge gains in the battery to 1 decimal place. Okay, so the energy that 1 coulomb gains is just how much energy like the battery produces. So it's 4.5. Okay, and the energy lost by 1 coulomb in the battery, so it's the electromotive force minus the potential difference. So it's going to be 0.4. And the energy that 1 coulomb of charge delivers to the bulb. So that's the energy at the end. Okay, so 4.1. A car is rated 70 ampere hour. What is the amount of charge traversing a circuit branch to the core battery? Okay guys, coulombs equals current times time. Also, coulombs also, this it's a second formula, it's not rated. It's joules per volts. So this is the same as the energy formula, because joules is just the energy. You can see this is the energy, and you could take it to the other side and take this to the other side. So basically, yeah, these two you guys should know them. So we're gonna use the current times time because they gave us current 70 ampere hour. So 70 ampere. And the hour, they want time in seconds. Time is always in seconds in this formula. So you're gonna do times 60 times 60 to find the minutes, then to find the seconds. So it's gonna be equal to let me do it on the calc. 70 times 60 times 60. 25200. So 25200. Consider the 4 circuits below. Select the circuit that contain 4 lamps in series. Okay, so in series means they're all like in a series, basically. I don't know how to explain this one. Series, this one. These ones are parallel. Basically, anything that doesn't branch off, okay, it's just one loop. That's series. Okay, parallel has multiple loops. So anything that's in one loop is series, multiple loops parallel. An ammeter should always be included in series because look, I'll tell you guys why. let's say you have a circuit, yeah, and you go like this. So the current ammeter, it measures current, yeah. So the current would actually split up. Some of it would go this way, some of it would go this way. So if you connect it in parallel, some of it would go to the ammeter, some of it would go to the circuit you're trying to measure. So it should always be in series with the circuit. Okay, let's say you have the ammeter here and this is the circuit. Okay, it's gonna be the same current flowing through the whole thing. But if you connect it in parallel, then it's gonna go like, and it's gonna split up. Okay, it doesn't always split up equally. It just splits up. Like if you have 4, it's not gonna go 2 and 2. It can go 2 and 2. It can go differently. Okay, depending on the circuit. But voltmeter, you guys would connect it in parallel because volts are the same in parallel, but in series it would be different. With the component through which the current, yeah, so the ammeter measures current, is to be measured. In the experiments, when objects are charged by rubbing, objects that behave like polythene are said to be. Polythene is plastic and like silk basically. So negatively charged, whereas objects behave like glass are said to be positively charged. Positive. Okay, a suspended neutral metal ball touches the rod made of material Y. When a charged rod touches the rod made of material Y, the suspended ball remains stationary. Choose the correct answer. Okay, rod Y is made of an... Okay, click. This is positive, yeah? And this is neutral. If this was a conductor, the positive charges would be in both of them. They would both be positive. And if this is positive and this is neutral, the electrons would go to this side and then the electrons would attract to the positive side, and I think they would go in here. So then this would be positively charged. So then this would repel if it was a conductor. But it doesn't move, so it is an insulator. Another term for earthing a conductor is grounding. The conductor in this part of the conductor is connected to a much bigger conductor. Guys, look, so earthing or grounding, let's say you have a circuit, yeah? Let's say you have a circuit. Okay, just a battery connected, it's actually just a lamp, okay? So this is a circuit, yeah? There's a charge flowing in it, yeah? A current flowing through it. But then if you connect it to a much bigger conductor, let's say the earth, for example, or like you touch it, because you're much bigger than it. So the current would spread out across like the whole earth, basically. So it would just remove the current. It's spread out over such a big area. So yeah, it wouldn't it would be gone. So yeah, you connect it to a much bigger conductor. In an experiment, a negatively charged rod is brought close to two neutral conducting spheres that touch each other. When one of the spheres initially standing further away from the rod is moved away, it is found to carry a charge. Oh, guys, this is induction. Let me just explain induction. Look, so you have this is a stand, okay? And you can move them in it. So you have two metal balls or conducting balls, spheres, okay? And they're neutral both. So then you bring a charged rod. Doesn't matter if it's positive or negative. Well, let's say it's positive. You bring it close to it, but they don't touch. Okay, so then the negative charge would go here towards the rod. If the rod was negative, this would be positive. and then the negative charge goes here, so that means this side is positively charged, right? So then if you separate them, this would be this ball would be positive, and this one would be negative. Okay, but you don't let this rod touch. Okay, that's how induction works. So charging by induction, the sphere that is moved away from the rod will be carrying a weight. So it's a negatively charged rod. So the sphere carried away from the rod will have the same rod, so it's negative charge. Because then this one's gonna be positive. Objects become charged when they gain or lose electrons. Electrons move, protons don't move around. Electrons have a negative charge, protons have a positive charge. An object that gains electrons acquires a negative charge because it gained electrons. Okay, the electroscope shown below was positively charged by a glass rod. The gold leaves of the electroscope spread out away from each other. When another rod W is brought close to the metal knob, the gold leaves, they come closer. Okay guys, like, so this one, electroscope was positively charged. So the electroscope, this thing, okay, it's positive, yeah? So then the negative charge, wait, this is positively charged, yeah. So now the electroscope is positive. Oh my god. Guys, wait, let me restart explaining this because I messed up. The electroscope is positively charged, yeah? The gold leaves, they spread out. When you bring another object, the gold leaves, when you bring W, the gold leaves, they come closer together. So the positive charge in the leaves is weaker. Why would the positive charge be weaker? Because it went up. What would make the positive charge go up? If you got a negatively charged object. If this is negative, then the positive charge would go up. So then the leaves, they would come closer together because there's less positive charge pushing them away. So the force repelling them is weaker. So W has to be negative. Okay, which of the following can be referred to as an electric current? The flow of negative charges or the flow of positive charges. By positive charge, they don't mean electrons. They just mean the charge. Like, look. Electrons move, yeah? Let's say you have an electron, yeah? It moves this way. So this side, the negative charge is moving this way. That means the positive charge is moving this way. Because this side is becoming positive if the electron left. It's not a proton moving, it's an electron leaving. Okay? And yeah, that's wrong. And the motion of neutral atoms, no, yeah. Okay, the electrons in the circuit, the electrons move from like the negative side to the positive side. The electrons, they're repelled from the negative and they go into the positive. So the electrons move from A to B. The conventional charge is the positive charge that I just explained in the question before. It's the electrons leaving, so it's going to go from positive to negative. So from B to A. The current in the circuit. So guys, what did I click? So the current Q equals IT. I times T. So 3 equals the current times 0.6. So I equals 5, I think. I equals 5. Just applying the formula. In order to move 2.5 coulombs of charge against the potential difference of 24 volts, guys, again, Q equals energy over voltage. So 2.5 equals x over 24. Shift solve. So 2.5 equals, you get 60. Equals 60 joules. Again, just applying the formula. 60. Okay, the power developed in the circuit. So power equals I times V. So 2 times 12, so power is P equals 2 times 12. So it's equal to 24. 24 watts. Okay, now guys, you know power, it's joules per second, yeah. Equals joules per second. So, and they gave us 5 minutes. So how many seconds is that? We can do it on your calculator. So P, so wait. P is 24. It's equal to joules over 5. So 5 minutes times 60 seconds. So also just put it on your calculator, shift solve. (24) equals x over 5 times 60. 7,200. So it would be 7.2 kilojoules. Wait. J equals 7,200. So you divide by 1,000 to get 7.2 kilojoules. 0.2. What is the energy supplied by a generator to transfer a coulomb of charge from the positive terminal to the negative terminal called electromotive force? That's the force supplied by the battery. Okay, that's the force that moves the charge. Okay. 2 resistors in and the bulb in. Okay, look. So guys, the 2 resistors, they're in one loop, so they're in series. I hope I spelled that right. And the bulb in parallel, because it's in another loop. Is that correct spelling? I don't know. We'll see at the end. Which of the following are true about measuring the electric current through an element in the circuit? The current is measured by an ammeter. The measuring device must be connected in series with it. The current through an element is measured with the same device as a potential difference. No. The measuring device must be earthed. No. The measuring device must be connected in parallel. No. It's the same as the question. There was a question a few questions back. Also the ammeter. Which of the following are true about measuring the potential difference? The measuring device must be parallel. Yeah. Guys, remember the other question I told you, voltage is the same in parallel, but current like splits up, but voltage also is different in series. Voltage splits up in series, but in parallel it's the same. Potential difference is measured by an ammeter, no, it's measured by voltage. Must be connected in series, no, it's fine. Okay, in the diagram below, the current through the resistor A is 1.1, the current through the resistor B is 0.3. The current through the battery is... Okay guys, look. So here the current was what? We don't know. And then it splits up into two. It splits up into 1.1 plus 0.3. So then it would come back together to go to the battery. So that's going to equal 1.4. It splits up to go, but yeah, it's current splits up. But when it comes back, it's the same. Like it splits up and then they came back together. So it's going to be 1.4. Okay. In the diagram below, the potential difference across the battery is 3 volts and the potential difference across the bulb is 1 volt. Okay guys, look. So the potential difference coming out of the battery is spread across the thing. Okay? So here you have 3 volts, they came out. And then here we have 1 volt. So it's 3 minus 1 volt. But here we have 2. But guys, remember, these are in parallel and volts is the same in parallel. Okay? So 3 minus 1 gives you 2. So if you remove the battery, you'd have 2 volts left. And these two, they're connected in parallel. So they're both 2. The 2 volts is going to be the same for both of them. If they were in series, it would be different. But they're in parallel, so they have the same voltage. And the remaining voltage is 2 volts, so it's going to go to both of them. Okay, particle S. Guys, look. The charge, it goes from positive to negative. So see how it's going, see this little arrow? It's going from S towards T. So S is positive and T is negative. Because the charge, it goes from positive to negative. Here, they're both positive because, see the arrow is pointed away. The positive goes away from the particle. If the arrow was pointed in, then they'd both be negative. But no, it's pointing out. So they're both positive. Okay, guys. A variable resistor is this, and it's just a normal resistor with an arrow through it. A cell is this. This is the battery. Well, by the way, guys, you should know this. The long side is the positive side, and the short side is the negative side. Okay. Lamp is this, and voltmeter is obviously the one with the V. So yeah. The force between two equal charges that are 2 centimeters apart is 1.2 millinewtons. If the distance between the charges decreased to 0.5 centimeters, the force between them becomes something millimeters. Okay, guys, look, so you have two equal charges. Let's say a positive charge and a negative charge. By equal, they mean negative 1 and 1, not negative 2 and 1. Okay? They're 2 centimeters apart. And this, it's 1.2 millinewtons. So now, they got them closer, yeah? So it's a positive and negative. Only 0.5 centimeters apart. So do you guys think the force here is going to be stronger, obviously, yeah? So they're not directly proportional. When the distance decreases, then the force increases. So they're inversely proportional. So it's going to be R or D1 for the distance 1 over D2 equals F2 over, but what's this? F2 over F1. Yeah, but guys, this, it would give you the wrong answer. You actually need to square this. You can either square the distance or square root the force. Okay, so this is the formula. D1 over D2 squared, the whole thing, okay, equals F2 over F1. Be careful, guys. D1 is not F1. If you put D1 here, then they're like the opposite. Okay, so let's solve it. So, what's D1? 2. What's D2? 0.5. So 2 over 0.5 squared equals F2. This is F1. So F2 is this one. So we'll split X over F1. So 1.2. And then you shift solve. You do it on your calculator. Just give me a sec. So 2 over 0.5 squared equals X over 1.2. You get 19.2. X equals 19.2. The answer is 19.2. 19.2.